Hi, I'm Mingyu from Shanghai Zhao University. I'm happy to share our work Platinum, a CPU-efficient concurrent garbage collector for tail reduction of interactive services. This is a joint work from Shanghai Zhao University and Alibaba Group. For ease of maintenance and deployment, applications in cloud have been split into small, single-purpose, and interactive services, so a single user request may rely on the cooperation of multiple services. For example, when a user wants to check out, he or she will go to the checkout page on his cell phone, which is actually rendered by many services, such as the coupon service to calculate the most cost-effective coupons, the cart service to list all items, and the recommendation service to recommend items the user might be interested in. Besides, those services may interact with cache services to retrieve data. Since Java has many advantages like portability and reliability, in Alibaba, most online services are written in Java, which means that those services are all managed by the Java runtime, the JVM. So, the performance of services will be affected by the modules in JVM. If a service is paused by JVM, other services will also be affected, and the user may find that the page fails to be loaded. Garbage collection is one of the cases where the applications should be paused. It is the automatic memory management module in language runtimes such as JVM. In JVM, private garbage collector is stop the word. As the execution flow shows, when application threads or mutators are running, GC threads are idle. When GC is triggered, all mutators will be paused so that GC threads can reclaim the memory. The advantage of the stop the word GC is that since all mutators are paused, GC threads can monopoly the CPU resources and achieve high GC throughput and satisfying CPU efficiency. However, since applications are paused during the whole GC, the latency, especially the tail latency for applications, will be affected. We have evaluated the coupon service in Alibaba to study the relationship between GC and application latency. We run the service for 30 seconds and collect the latency for each request. In the left figure, each black dot stands for a request, and the vertical red line stands for garbage collection. When a GC pause happens, the latency of a request fluctuates dramatically, and as the right figure shows, those requests cause a long tail of the execution. Note that the coupon service is running with other services, so it also interacts with others through the network, and it also uses disk I/O to access files. However, our evaluation shows that GC is the killer factor for tail latency. Since GC pauses affect the tail latency of services, a solution is to allow mutators to execute during garbage collection. This kind of GC is called concurrent GC. Concurrent GC can be classified into two categories: partial concurrent and mostly concurrent. Partial concurrent GC allow mutators to execute in some phases in GC. A typical example is G1. As the execution flow shows, in the first part of GC, mutators can run concurrently with GC threads, but for the second part, the mutator will have to pause. To reduce the duration of the stop the word pauses, partially concurrent collectors provide arguments for user to tune the maximum limit on GC pauses. The second category is mostly concurrent collectors, and the typical example is Shenandoah GC, which is a new GC in OpenJDK. In most concurrent collectors, mutators can execute in nearly all GC phases. As the execution flow shows, mutators only need to pause for a very short time when GC threads try to achieve some synchronization points. Since concurrent GC can reduce the duration of pauses, is it always helpful to reduce the tail latency? We have evaluated those two kinds of GC with a straightforward workload in the coupon service. For G1, we tune its argument maximum GC pause millisecond to restrict the maximum GC pause time. When we reduce the argument from 60 milliseconds to 30 milliseconds, the minimum and the average GC pause decrease. However, the number of GC is enlarged by 5 times, and the accumulated GC time actually increases. This means that GC threads are consuming more CPU resources, so the average CPU utilization also increases. As a result, although the argument is helpful to reduce per GC pause time, the tail latency actually becomes worse. For the mostly concurrent GC, the situation actually becomes worse. We have evaluated Shenandoah with the same workload as G1. Compared with G1, the 30 millisecond setting, the GC pauses in Shenandoah are much shorter, both the minimum GC pause and the average GC pause. However, its GC duration is quite long. The duration of the evaluation is 60 seconds, while the GC threads are active in more than 53 seconds for Shenandoah. So the average CPU utilization in Shenandoah is quite high. And as a result, the tail latency for Shenandoah is even worse than the worst setting, the 30 millisecond setting of G1. We have listed 3 important reasons on why concurrent collectors are less efficient than stop-the-word garbage collectors. First, in stop-the-word GC, GC threads can monopoly all CPU resources. But for the concurrent GC, GC threads have to share CPUs with mutators, so GC threads get less resources for collection. Second, since GC thread and mutators are running simultaneously, it is possible that they are accessing the same object at the same time. So, GC threads have to synchronize with mutators to ensure correctness, which leads to more runtime overhead. Third, for mutators, before they read or write an object, they have to make sure that the object is not copied or modified by the GC threads. So mutators have to instrument the code before ever read or ever write operations, which is called barrier code. As the example shows, before modifying the object y, a mutator has to check if y is being collected. If so, it needs to call into a slow path. This part is called barrier code. The barrier code needs to be added into every read or write operations, so it will introduce runtime overhead. Given those 3 problems, our question is, can we design a collector with both low latency and high CPU efficiency? We have found some opportunities to design such a new garbage collector. The first one is idle calls during GC. Even for the stop-the-word GC, since the GC algorithm is like a graph traversal on objects, so the workload for each thread is unknown before processing, and it is hard to achieve load balance. We have evaluated SpecJBB 2015, a simulated online supermarket service with 80 logical cores. We find that even for parallel scavenge, a stop-the-word GC OpenJDK, its GC performance remains stable when reaching 30 cores. OpenJDK is aware of the scalability problem, so its default setting uses less GC threads than the number of cores. For example, the default GC thread number with 80 cores is 53, which means that the other 27 cores during GC are idle. The second opportunity is skilled write behavior. As the figure shows, the interactive services process requests in sessions. When a request is received, a session begins. When a response is sent, the session ends. When the session is active, the service will allocate objects and manipulate them. Of course, the service also modifies shared data structures, but it is unlikely to manipulate objects in other sessions. So, we assume interactive service may have skilled write behaviors. When a session is active, most write will fall into the new objects created by the session. We call the memory span a working set. We have evaluated different services. Cassandra, a key value store, Coupon and Shop Center are online services in Alibaba, and SpecJBB, a simulated supermarket. Those services share similar write behaviors, which means that very few writes fall out of the working set. But for other applications like Spark, a big data processing framework, the memory behavior is quite different. The session in Spark will incur many writes outside the working set. The last opportunity is the development of hardware features. MPK, or memory protection keys, allow users to configure differentiated page permissions within a process. For example, we can divide virtual pages in a process into 3 domains and configure the threads with different permissions on those domains. For example, 3.1 has read-write permissions to the domain 0, and 3.2 has only read-only permission to the domain 0. Previously, MPK is mainly used to achieve isolation and security between threads. But our question is it possible to use MPK also for performance? We propose Platinum, a mostly concurrent collector with moderate CPU consumption. As the execution flow shows, Platinum is a 3-phase collection algorithm. The first phase is an initial pause when Platinum needs to initialize the collection. It is quite short and takes less than 1 millisecond. The last phase is also a pause to update some stale references, which takes about 10 milliseconds. The middle part is the concurrent phase, where mutators can run simultaneously with GC threads. Note that mutators in the concurrent phase execute with restrictions, which is a major difference between our work Platinum and private GC. Platinum mainly contains 3 design highlights. First, it collects idle cores and not used by GC threads and gives them to mutators. Second, it partitions the heap to isolate memory between GC threads and mutators and minimize the inter-thread synchronizations. Third, it uses MPK to remove the need for barriers. We will introduce those 3 parts respectively. As for CPU, Platinum first uses the Linux schedule set affinity API to bind GC threads to separated cores. In this way, each GC thread can monopolize its core during GC. Since the number of GC threads is smaller than the number of cores, other cores not used by GC threads are identified as idle cores by Platinum. When GC is triggered, Platinum also changes affinity on mutators so that they can only execute on idle cores. This mechanism isolates the cores used by mutators and GC threads, and CPU contention is avoided. For the heap memory, according to the aforementioned skew-right behavior, Platinum partitions the heap into 3 areas. The first collection area contains objects which require to be collected. The pin area contains objects allocated by the active sessions, so they are frequently manipulated by mutators and should not be collected. The allocation area is reserved for mutators so that they can allocate new objects during GC. After partition, Platinum has enforced isolation for GC threads and mutators. For GC threads, they can only collect objects in the collection area. If they find that an object in the other 2 areas, the pin area or the allocation area, it will treat it as a newly created object and avoid touching it. For mutators, since they follow the skew-right behavior, they will mostly access the pin area and the allocation area. This design makes mutators and GC threads focus on their own memory part and minimizes the synchronizations between them. However, the heap partition can only guarantee that mutators mostly modify the pin and the allocation area. It is still possible for mutators to access and modify the collection area and cause data races. A traditional solution is write barriers we mentioned before. For example, we can check if an object is in the collection area before modifying it. If so, we can use a slow path to make sure that the write operation can correctly synchronize with GC threads. However, this solution requires instrumenting every write operations, which is quite costly and unnecessary. Platinum instead uses an MPK-based hardware protection mechanism. It further divides the heap into 2 MPK domains. The collection area is in the first MPK domain, while the pin and allocation area are in the second MPK domain. Then, Platinum also configures the permission on mutators, so they only have read-only permission for the domain 1, while GC threads have read-write permission to both 2 domains. In this way, if a mutator tries to modify an object in the collection area, it will trigger a page fault, and the pre-register handler in Platinum will handle this write correctly. For the detail of the page fault handling, please refer to our paper. We evaluate Platinum with the 80-core machine, with 3 other collectors as baseline. Concurrent mark sweep, or CMS, is a classic partially concurrent collector, and its pause time is relatively large. Garbage first, or G1, is a highly tunable partially concurrent collector, which becomes the default GC in OpenJK9. In the evaluation, we have tuned G1 to reach its best latency for each application. Shenandoah is a mostly concurrent collector, which is a new collector in OpenJDK. And as for applications, we use different applications for our evaluation. SpecGB 2015 is a simulated online supermarket which can be seen as a web service. Cassandra is a key value store, which can be treated as a storage service, and the coupon is a real online service in Alibaba. As for SpecGBB 2015, we have tested with different throughput settings, ranging from 1,000 to 40,000. The results show that Platinum has better 99 latency than CMS in all settings, and can reduce the 99 latency by up to 79.3%. Platinum also has comparable 99 latency with our tuned G1. As for throughput, Platinum has the best maximum throughput among all collectors, which suggests that Platinum has great CPU efficiency and can stand very high throughput. For Cassandra, we evaluated with two YCSB workload settings: read intensive, which contains 76,000 reads and 4,000 updates per second, and write intensive, which contains 40,000 reads and 40,000 updates per second. For the read intensive workload, Platinum has comparable tail latency with Shenandoah and beats G1 and CMS. But for the write intensive workload, Platinum performs worse because write operations require introducing more modifications on the global data structure, which is outside working set, so the number of page fault will increase. However, in the write intensive workload, Platinum still performs better than CMS. And for the coupon service in Alibaba, we evaluate with the production traces. The result shows that Platinum has better tail latency for G1 and CMS. As we mentioned before, since the application latency in Shenandoah is much worse than others, so we do not show its latency in this figure. Finally, we will also show the average CPU utilization under stressful workload for different services. The result shows that CMS actually introduces moderate CPU consumption. This is because it introduces relatively long pauses and reaches satisfying GC efficiency. However, as we showed before, its tail latency is quite high and worse compared with other collectors. Compared with G1 and Shenandoah, Platinum has better CPU utilization, which confirms that Platinum can achieve both low latency and moderate CPU consumption. Okay, to conclude, private collectors make a trade-off between latency and CPU efficiency. We therefore propose Platinum to break this trade-off. And it provides three design points to preserve low GC pauses while reducing the overhead in private collectors. They are idle core collection to mitigate the CPU contentions between GC threads, and heap partition to minimize the synchronization between GC threads and mutators, and MPK-based barrier elimination, which uses the recently released MPK hardware feature to reduce the runtime overhead. And the evaluation on different interactive services show that Platinum can achieve both low latency and moderate CPU consumption compared with private garbage collectors. That's all. Thank you for listening.